Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the energy equation of steady flow process. The term steady and uniform are used often in engineering, and thus it is important to have a clear understanding of their meanings. The term steady implies no change with time. The opposite of steady is unsteady or transient. The term uniform, however, implies no change with location over a specified region. These meanings are consistent with their everyday use. A large number of engineering devices operate for long periods of time under the same conditions, and they are classified as steady flow devices. Processes involving such devices can be represented reasonably well by a somewhat idealized process called the steady flow process, which can be defined as a process during which a fluid flows through a control volume steadily. During a steady flow process, as the figure shows, fluid properties within the control volume may change with position, but not with time. Steady flow conditions can be closely approximated by devices that are intended for continuous operation, such as turbines, pumps, boilers, condensers, and heat exchangers, or power plants, or refrigeration systems. The fluid properties can change from point to point within the control volume, but at any fixed point, they remain the same during the entire process. Therefore, the volume V, the mass M, and the total energy content E of the control volume remains constant during a steady flow process. Some cyclic devices, such as reciprocating engines or compressors, do not satisfy any of the conditions stated above, since the flow at the inlet and the exit will be pulsating and not steady. However, the fluid properties vary with time in a periodic manner, and the flow through these devices can still be analyzed as a steady flow process by using time-averaged values for the properties. Energy transmission with a rotating shaft is very common in engineering practice. The topic of this subtask is about the shaft work. Shaft work is proportional to the torque applied and the number of revolutions of the shaft. Often, the torque T applied to the shaft is constant, which means that the force F applied is also constant. For a specified constant torque, the work done during N revolutions is determined as follows. A force F acting through a moment arm R generates a torque T of. This force acts through a distance S, which is related to the radius R by. Then, the shaft work is determined from the power transmitted through the shaft is the shaft work down periodic time, which can be expressed as. The topic of this subtask is about the energy equation of steady flow. The fluid properties at an inlet or exit remain constant during a steady flow process. The properties may, however, be different at different inlets and exits. They may even vary over the cross-section of an inlet or an exit. However, all properties, including the velocity and elevation, must remain constant with time with a fixed point at an inlet or exit. It follows that the mass flow rate of the fluid at an opening must remain constant during a steady flow process. As an added simplification, the fluid properties at an opening are usually considered to be uniform over the cross-section. Thus, the fluid properties at an inlet or exit may be specified by the average single values. Also, the heat and work interactions between a steady flow system and its surroundings do not change with time. Thus, the power delivered by a system and the rate of heat transfer to or from a system remain constant during a steady flow process. For a steady flow process taking a period of time tau, and it is assumed that exactly 1 kilogram of fluid flows through the system during this period, and at the same time heat Q is added and shaft work WSH is done. The terms in the first law of equation 2.4 are the heat and the total energy change of the system are the total energy change of the mass flow is. The total work is. Based on equation 2.4, we have energy equation for the steady flow process. This is equation 2.13. It is applicable for steady flow open system, any working fluid, and any process. For flowing working fluid, enthalpy can be understood as the sum of the internal energy and driving work of the fluid transmitted. The energy balance relation just given is intuitive in nature and is easy to use when the magnitudes and directions of heat and work transfers are known. When performing a general analytical study or solving a problem that involves an unknown heat or work interaction, however, we need to assume a direction for the heat or work interactions. In such cases, it is common practice to assume heat to be transferred into the system and work produced by the system, and then solve the problem. Okay, that's all for this task. Thank you very much, and see you next time.